So, we are discussing about the solutions of the homogeneous second order linear ODE. We have seen few properties. Two solutions when they are linearly independent, we have seen that they are linear, two solutions are given. So, they are linearly independent if and only if the Wronskian of them should be non-zero. Okay. So, and you also have seen that if the Wronskian is 0 at one place, that means the Wronskian is 0 everywhere, and similarly if it is non-zero, it is non-zero everywhere. At one place if it is non-zero, it should be non-zero everywhere. And so, using we also derived the Abel's formula. Through that we showed that property, if the Wronskian is 0 or non-zero, implies at one place implies 0 or non-zero everywhere. So, if from the Abel's formula we could also derive, if you are given one solution y1, you can find the other y2 through the formula, Abel's formula. And also we have also seen another property that the second order linear homogeneous ODE will have only two linearly independent solutions. That means any solution you can represent in terms of these two linearly independent solutions. Suppose you are given y1 and y2 which are linearly independent solutions, that means you know all the solutions. Okay. So, now the question is, how do we find these solutions? How do you find these linearly independent solutions y1 and y2? Okay. So, certain forms, if your homogeneous linear second order ODE has certain form, for example with constant coefficients, you can easily find linearly independent solutions. Okay. Start with let y double dash plus, so let us say some constant a, y dash plus some constant b, y equal to 0, where a, b belongs to R. If I take this and x belongs to full R or some I that is part of R. Okay. Then how do we solve this equation? So, y of x. So, we know that we have seen if it is a first order equation with some constant coefficient, what is its solution? This has a solution e power minus ax. We have seen this one, okay, as a solution e power minus ax. So, it has exponential solutions, it is natural exponential of some constant times x. So, we look for same way. So, having known first order equation, first order linear ODE with constant coefficient, a is constant, it has a solutions, exponential solutions. This will give us a hint to imagine that the second order equation also will have such solutions. So, by answers, let us try, let y of x be e power some constant, this constant you may not be knowing, you call this lambda x, okay, for some lambda belongs to R. Okay. So, if you assume in this form, if you want you are looking for solutions in this form. So, this you substitute into the equation, y double dash is lambda square e power lambda x plus a times lambda e power lambda x plus b times e power lambda x equal to 0. This gives me e power lambda x into lambda square plus a lambda plus b equal to 0. Since e exponential cannot be 0, then this has to be 0. Okay. So, this implies lambda square plus a lambda plus b equal to 0. This will give me lambda, you can find the roots of this quadratic equation, minus a plus or minus square root of a square minus 4 1 into b, 4b divided by 2 is 1. Okay. So, these are the two roots of these quadratic equations. Once you know this lambda 1, so you assume that lambda 1 lambda 2. So, lambda 1 lambda 2, then the solutions are e power lambda 1 x and e power lambda 2 x. If lambda 1 lambda 2 are different, certainly these two solutions are linearly independent, right. So, you divide it, it is not a constant. Okay. So, this is your y1, this is your y2. So, if you divide y1 by y2, it is not a constant if lambda 1 is not equal to lambda 2. What if lambda 1 equal to lambda 2? If lambda 1 equal to, there are only two cases. You have two roots, these are the roots, either they are not equal to, they are not same, or they are same. So, if they are not equal, lambda 1 lambda 2 not equal implies you have two solutions, one is this, other one is this, okay, and they are linearly independent clearly, okay, because y1 by y2 is not a constant if lambda 1 is not equal to lambda 2. So, other case is lambda 1 equal to lambda 2. So, this will give me y1 of x is e power lambda 1 x, okay. So, what is the other solution? If you use as y2 as e power lambda 2 x is actually same, you divide it y1 by y2 which is constant because lambda 1 equal to lambda 2. So, you are not getting second linearly independent solution, okay, but you already know how to get your second linearly independent solution having known one solution, one non-zero linearly independent solutions. Non-zero implies linearly independent, okay. So, this we do not take it as y2, okay. So, this is your y1. So, we can find other linearly independent solution by the method, by the earlier method. Okay, so, using Abel's formula you can find the other solution. So, these are the only two parts you have. So, let us do some examples. Some examples if you do understand. So, how do we do this? Examples. So, let me pick up some simple solve y double dash plus y dash minus 2y equal to 0. How do we solve this? So, you look for e power lambda x, let y of x is this, then you have lambda square plus lambda minus 2 equal to 0, because a equal to 1, b equal to minus 2. So, lambda square. So, this is what is the equation. So, this will give me the roots lambda which is equal to minus 1 plus or minus square root of 1 8 divided by 2. So, this will give me minus 1 plus or minus 3 by 2. This will give me 1 with plus and minus 2 is the second root. So, these are the two roots, okay. Since lambda 1 equal to 1, lambda 2 equal to minus 2 and lambda 1 is not equal to lambda 2, this implies you have y1x is, you put instead of lambda what you found, your lambda 1, okay. Instead of lambda you put lambda 2. So, you have e power x is one solution, y2x is e power minus 2x is another solution. These are two linearly independent solution. That implies any solution yx should be a linear combination of y1 y2. So, this is c1 some constant times y1x plus c2 y2x. So, this implies yx equal to c1 e power x plus c2 e power minus 2x. So, this is your solution. Any solution will be in this form. This is exactly what you have. So, you have a two arbitrary constants c1 and c2 for the second order equation, second order homogeneous linear equation. You know that we have seen linear equation will have unique solution for all values of x, and we have found this general solution because the second order you have two arbitrary constants c1 and c2, and we have seen this. We already have in this form two linearly independent solutions. If you get, you can combine with an arbitrary constant, there is also a solution. So, it has two already, this form c1 e power x plus c2 e power minus 2x is already having two arbitrary constants. That implies this is the general solution. this is the general solution. Okay. So, this is how we solve this case. Now we solve another type of equation. So, example 2, we solve y double dash plus 2y dash plus 4y equal to 0. How do we solve this? So, again it is a equation with constant coefficients, x belongs to R. Okay. So, let us solve this. Let y of x is let y of x equal to e power lambda x. So, if you substitute, this will give me lambda square plus 2 lambda plus 4 equal to 0. So, this will give me lambda equal to minus b plus or minus square root of b square minus 4 into 4, 16 divided by 2. So, this will give me minus 1 plus or minus root 12, okay, by 2. So, this will give me minus 1 plus or minus root 3. Okay. So, these are your solutions. So, lambda 1 equal to minus 1 plus root 3, lambda 2 equal to minus 1 minus root 3. Okay. So, you clearly these are different, and lambda 1 is not equal to lambda 2. So, this will give me the general solution like in the earlier case, C1 times e power minus 1 plus root 3 into x plus C2 times e power minus 1 minus root 3 into x. Okay. So, this is actually equal to, you can e power minus x is common in both terms. So, you have C1 e power root 3x plus C2 e power minus root 3x. Okay. So, this is your general solution, this is the general solution. So, we will see the case where these roots are same, as an example 3. So, your simple thing is 4y dash plus 4. So, you solve it, you solve this one. So, you can clearly see that if you follow the same technique. So, by choosing y of x equal to e power lambda x. So, lambda will satisfy lambda square plus 4 lambda plus 4 equal to 0. That will give me lambda equal to lambda plus 2 whole square equal to 0. That will give me lambda equal to minus 2 and minus 2. So, these are the repeated roots, lambda minus 2 and minus 2. So, y1x is e power minus 2x, and y2x is also e power minus 2x. So, y1 by y2 is actually 1 constant. So, if I cannot choose this as a second linear independent solution y2. So, you know by earlier method, how do I find my earlier method by Abel's formula? You know, if you are given one solution y1, I have given you this solution. So, you can find the other solution y2 as y1x, that is e power minus 2x, an integral x naught to x naught is in the domain, is x naught from any point in the domain. So, you have a full real line. So, I can choose it as 0 to x e power minus integral x naught to t pt dt. P is 4 here. So, you have 4 here. So, 4 dt divided by p1 y1 of t square. So, y1 is e power minus 2t, y1 of t is e power minus 2t. So, you have a square is e power minus 4t dt. Okay. So, this is actually ds and this will be dt. So, this is your second solution from the earlier formula. So, if you actually calculate e power minus 2x integral 0 to x, and this will be e power minus 4t divided by e power minus 4t into dt. So, this is nothing but simply e power minus 2x integral 0 to x dt. This gets cancelled. So, you have simply x e power minus 2x. So, this is your y2. Okay. So, this is your y2x. So, y2x is x into e power minus 2x. You can clearly see the pattern. If you have one exponential function, if you have a repeated roots, one solution is e power minus 2x, other solution is simply multiplication with x. So, you have one solution is this, other solution if they are repeated roots simply multiply x, okay, x into that will be a solution. So, the general solution of the given equation is yx equal to c1 e power minus 2x plus c2 x into e power minus 2x. Okay, so, e power minus 2x common. So, you have c1 plus c2x. So, this is your general solution. This is how you see when the roots are same. So, we know now how to solve homogeneous equations, how homogeneous linear equations with constant coefficients of second order. Okay, second order linear homogeneous equations, you know how to solve. When you substitute solution of the form e power lambda x, then lambda satisfies a polynomial of degree 2 that will have two roots. When the roots are different, you will have easily there are two linearly independent solutions, and when they are same, you have only one linearly independent solution e power lambda 1x. Other solution is just multiply x into e power lambda x is also another solution. So, that you can see given, so you know one solution e power lambda x, lambda 1x, and then once you know one solution you can use the method to find the other which you learned earlier, or you just look for solutions, or you simply if your lambda square plus a lambda plus b equal to 0, if has a repeated roots, okay, implies lambda equal to lambda 1. If suppose lambda 1 lambda 2 are same, then e power lambda 1x is one solution, x into e power lambda 1x is another solution. So, what is your equation? So, equation is y double dash plus ay dash plus b, ab are constants, by equal to 0. So, this is your equation, and once you substitute your y of x as e power lambda x, then lambda satisfies, if lambda is this, then lambda satisfies this, which has the roots lambda 1 lambda 2, when they are same lambda 1 lambda 1. So, this is one solution clearly. The second solution you have seen that it can be like this, that you can easily see. So, by substituting, you just substitute into the equation. Once the repeated roots are repeated lambda 1, you can simply x into e power lambda 1x, you simply take it as your y2 of x. Okay. So, this gives me y2 dash of x, you can calculate, that is e power lambda 1x plus lambda 1x e power lambda 1x, and your y2 double dash is again e power lambda 1x into, so this is into lambda 1 plus lambda 1 e power lambda 1x plus x into lambda 1 square e power lambda 1x. Okay, so this is what you have. So, if you substitute, you get lambda 1 e power lambda 1x. So, these are 2 times 2 of this plus x into lambda 1 square e power lambda 1x, and then plus a times e power lambda 1x plus a times lambda 1 x e power lambda 1x plus b times x into e power lambda 1x. I just substituted your y2 dash, y2 double dash, and you want to see what happens to this. This is equal to so x into e power lambda 1x, you take it out. If you take it out, you get lambda 1 square plus you have what happens a lambda 1 from this, and then plus b. This we know that this is 0, okay, because lambda 1 is the root of this equation. So, this is 0 plus what is the other thing, e power lambda 1x. This is e power lambda 1x. If you look at it, this will become e power lambda 1x is a plus 2 lambda 1 okay, a plus 2 lambda 1 equal to 0 equal to. So, this is what you have. So, this is equal to this. So, we have seen that lambda is the root of lambda 1 is the root of the quadratic equation. So, this is 0. Okay. So, what you have is e power lambda 1 x plus 2 lambda 1 plus a. Okay. If these roots are lambda 1 square, so lambda square plus a lambda 1, okay, plus b is actually equal to lambda 1, sorry, so what you should write, so this is equal to lambda minus lambda 1 whole square. Now, if you put lambda 1, this is 0, okay, both sides, left hand side and right hand side 0. If you differentiate dd lambda of this lambda plus a lambda plus b, that is actually 2 into lambda minus lambda 1, okay. So, that is so now if we put lambda equal to lambda 1, so lambda equal to lambda 1, then it is also 0. So, you can see that if you differentiate twice, what is this left hand side? Left hand side is actually equal to 2 lambda 1 after putting lambda equal to lambda 1 plus a. So, this is also 0, okay. So, this will become 0. So, this once this is 0, so you have simply 0. So, you can see that this is y2 any x into e power lambda 1 x is also a solution. So, this will be useful. This way of looking at the second solution is useful if you are when you are looking at higher order equations with constant coefficients. Whenever a root is repeated a few times, you differentiate n. So, if it is repeated k times, you differentiate up to every time. So, d k d lambda power k times. If you differentiate, it will still be, when you put lambda equal to lambda 1, it will be 0. So, that means, so that is what all those derivatives, this equation when you put lambda equal to lambda 1 and its derivatives dd lambda when you put lambda equal to lambda 1, dd lambda of that polynomial, okay, and then you put lambda equal to lambda 1, whatever comes will be there. So, up to k derivatives of the polynomial, okay, and you put, once you put lambda equal to lambda 1, that is what you will get once you substitute your x power k into e power lambda 1 k, lambda 1 x, okay. If you substitute, all these things are 0, so that makes it is a solution. So, if you have for the nth order equation, if you have roots are repeated lambda 1 lambda 1 lambda 1 k times, e power lambda 1 x is one solution, x into e power lambda 1 x is also a solution, because right, you like this. And third thing is, third solution you need x square into e power lambda 1 x, that is also a solution. Like that you can go on up to get x power k minus 1 into e power lambda 1 x, okay. That is also a solution you can show just by putting into the equation, because of the property that in the polynomial, if you have k roots, this will be lambda minus lambda 1 power k, okay. So, then if you differentiate up to k minus 1 times, it will be 0. So, that is what you are going to use, okay. So, using that property you can show that all this x power k is between k is repeated roots, k is k number of times lambda 1 is repeated, you have k power, you have 1 x and so on up to x power k minus 1 multiplied with e power lambda 1 x are the solutions, okay. So, each of these 1 x square up to x power k minus 1, all these things you multiply with e power lambda 1 x, which is repeated root. When lambda 1 is a repeated root, you multiply e power lambda 1 x to all these polynomials, like say 1 x square up to x power k minus 1. These are your solutions. Like that you can get your second solution if it is a second order, nth if it is nth degree polynomial, nth degree equation with constant coefficients. You still again look for e power lambda x as a solution, and if the roots are distinct, they are different, you can simply get all the n linearly dependent independent solutions. If they are repeated k times, some are repeated k times, then that particular root e power lambda 1 x, let us say lambda 1 is repeated k times, e power lambda 1 x and x into e power lambda 1 x up to x power k minus 1 into e power lambda 1 x are the solutions, okay. So, this is what you can easily see. So, you know how to solve the second order linear homogeneous equation with constant coefficients. Let us see. So, before we can also do extend this technique to higher order. Before I do this, I'll give you the we'll take the nth order linear equation and we'll look at the properties as the way we have seen for second order. So nth order equation is yn plus let me write I take this general form a1x into yn minus 1. This if I write y superscript in the brackets, that means dny by dx power n. So this is the nth derivative of y, and a2x y of n minus 2, and like that you have up to a n of x y equal to 0. So this is your nth order linear equation, okay, with coefficients or not, it's varying as a functions, okay. So if you have this, so as usual we look at the properties the way we have seen for the second order. So what are the properties? 1. So if y1 and y2, if you are given y1, y2, yn are n solutions, okay, if these are solutions of so let me call this L is an operator on y, okay. So where L is, so you can write this dn by dx power n, okay, so plus a1x dn minus 1 by dx power n minus 1 up to a n of x into just y, okay. You act on y, then this will become an equation, okay, Ly equal to 0. Solutions of Ly equal to 0, if I write, then a linear combination of this ci yi, so I is from 1 to n. You take a linear combination, multiply with some constant, any arbitrary constant ci, and you take the sum, is also a solution, So you can easily see, you just substitute, just how do you calculate, then yx, which is equal to, this is also a solution. So how do you do this? You calculate y and y dash, y and derivatives, because these are constants, ci's are constants, the derivatives are nothing but yi power n. So you substitute into the equation, you can see that this also satisfies the equation. So that is how, as you have seen in the for the second order, that's easy to check, okay. The second one is, if you are given n solutions, okay, let y1, y2, yn be n solutions of Ly equal to 0. So when do you say that they are linearly independent? y1, y2, yn are linearly I'll write the equivalent form. So linearly dependent if and only if, okay, if and only if the Wronskian, I will define the Wronskian of y1, y2, yn of x. This is actually determinant of y1, y2, yn. You take this as y1, y2, yn. So like a matrix, first row is you take y1, y2, yn, y1 dash, y2 dash, yn dash. You go like this up to y1 n minus 1th derivative, y2 n minus 1th derivative, up to yn n minus 1th derivative. So if this is equal to 0 for some x naught belongs to I, okay. So if your domain is I, that is part of real line, you have this is what you will have. This is also easy to show the way we have seen. How do I show? If you can see this, we will just demonstrate for n equal to 3, this one, this is easy to demonstrate for 3, if they are linearly dependent. What do you mean by dependent? y1, y2, y3 are linearly dependent means what? We have seen if it is two functions y1 and y2, they are linearly dependent only. So what is the definition? y1 by y2 is constant. That means one you can write in terms of the other. If you have three functions like this, y1x, y2x and y3x, these are linearly dependent if any one or any, if you take any one of them, you can write that in terms of other with some non-zero coefficients, okay. That means, so that you can write as a definition is, I can write any one of them. So for let us say y1, I will be able to write some c1 y2 of x plus c2 y3 of x with both c1 c2 are not 0. That means I will have some non-zero c1 and c2, okay, such that, so that means I am actually able to write 1 into y1x plus c1 y2x minus, okay, minus c2 y3x equal to 0. So, you see that not both c1 and c2 are 0, one cannot be 0. So, you see that some of them with some non-zero coefficient such that the linear combination of y1 y2 you will be able to make it 0. If you can do that, then these y1 y2 y3 are linearly dependent. Okay. So, that is what is the meaning of linearly dependence for three functions. If they are that is the case, what you consider is, if they are linearly dependent, what you do is you consider, suppose they are linearly dependent. So, you take the same. So, you take this y1x minus c1 y2x minus c3 y2x equal to 0. You differentiate because y1 y2 are satisfying, they are the solutions of a second third order differential equation because n equal to 3. So, you can differentiate twice. So, you get y1 dash minus c1 is constant. So, y2 dash c3 y3 dash of x is 0. Similarly, you can do one more time because it satisfies nth order differential equation. You can do 2 more times minus c1 y2 double dash of x minus c3 y3 double dash of x equal to 0. So, what is this? This is equivalent to this matrix, that is y1 y2 y3 at every value of x. Okay. This is at every value of x, y1 dash y2 dash y3 dash y1 double dash y2 double dash y3 double dash of some non-zero function 1 minus c1 minus c2. You can see that I have already from the definitions, not both the c1 and c2 are 0. So, I have some non-zero coefficients, okay, such that you see the right hand side is 0. So, this is the matrix like Ax equal to 0. So, I have a solution, non-zero solution 1 minus c1 minus c2. That implies the determinant has to be 0, you know. Okay. So, that means this determinant is of y1 y2 yx, y1 y2 y3, y1 dash y2 dash y3 dash, y1 double dash y2 double dash y3 double dash. Okay. Is actually equal to Wronskian of y1 y2 y3 of x equal to 0. This is actually true for every x. Okay. This is one way of proof. If you know that this is if you assume that they are linearly dependent. So, I proved that the Wronskian is 0. Okay, the Wronskian is 0. So, I may prove this way. So, assume that Wronskian is 0 at some point. I want to check whether y1 y2 y3 functions are linearly dependent. This is what you want to prove. Okay, check this if Wronskian of x naught is 0. Okay. Then, so what you do is, so you just make a linear combination of this y1x plus c2 y2x plus c3 y3x equal to 0 for every x belongs to I. So, once you make this, you can differentiate, you can have same like the earlier, you can differentiate plus c3 y3 dash of x equal to 0. And then you can also differentiate twice y1 double dash of x plus c2 y2 double dash of x plus c3 y3 double dash of x equal to 0. So, what is this one? This means I have this system y1 y2 y3 y1 dash y2 dash y3 dash y1 double dash y2 double dash y3 double dash with this c1 c2 c3 equal to 0 0 0. Okay. So, the same constant. So, if I fix, if this is true for every x for some c1 and c2 c3, it is also true for some x naught for an individual x naught for which this Wronskian is 0. So, you make this matrix at x equal to x naught. Okay. This matrix at x equal to x naught, if I put it y1 at x naught, y2 at x naught, y3 at x naught, y1 dash, all the derivatives are at x naught. You know that this determinant is 0. Okay. This determinant is 0 implies I can get c1, c2, c3, which these are the same constant comes from this system, which are non-zero. Okay. This is non-zero since the Wronskian at x naught is 0. It's like A, this is your A x equal to 0 matrix. Okay, this is the vector, this is the matrix, 3 by 3 matrix vector. So x equal to 0. If A is the determinant of A is 0 means the Wronskian is 0. So I have a non-zero solution, that is C1, C2, C3. So the same. So what I get is this C1, C2, C3. I find some non-zero C1, C2 such that its combination is 0. That is exactly the definition of linear dependence which I introduced. So implies y1, y2, y3 are linearly dependent. So once you do this property for the solution, 3 solutions for the third order differential equation, nth order differential equation, it's not difficult. You can do the same, you can follow the same procedure. Instead of working with this 3 by 3 system, you will have to work with n by n system. So what is the third property you learned? So the third property you learned is for the second order systems is Abel's formula. So okay, the third problem. So here also we work with n equal to 3. What is the Wronskian of x? y1, y2, x is actually y1, y2, y3, y2, y1 dash, y2 dash, y2 dash, y3 dash, y1 double dash, y2 double dash, y3 double dash, this determinant. So what is the meaning of derivative? So d dx of wx, d dx of wx, y1, y2, y3 are 2 solutions. You make this Wronskian. Okay, so if you do this, the derivative, once you differentiate, you want to differentiate the determinant. So what is the procedure? Every time you differentiate each row with respect to x and add up, next time the sum of the determinants in which each row is differentiated x with respect to x. So you just write, if it is a 3 by 3, so what I have is y1 dash, y2 dash, y3 dash, the rest of the 2 rows as it is, that is y1, y2, y3 dash, y1 double dash, y2 double dash, y3 double dash, plus now I differentiate the second row. So y1, y2, y3 as it is. The second row is y1 double dash, if I differentiate, y2 double dash, y3 double dash. This third row is as it is, y1, y2, y3 with double dashes. Now what I should do, the third row, third determinant should be first 2 rows as it is, y1, y2, y3. Second row is as it is, y1, y2 dash, y3 dash. Third row you differentiate 3 times, y1 triple dash, y2 triple dash, y3 triple dash. What is your equation? y3 derivatives plus a1x, y2 derivatives plus a2x, y1 derivatives, that is dy by dx plus a3 of x y equal to 0. So this is your equation. So you substitute here. So this 3 is minus a1x y2 derivatives minus a2x 1 derivative minus a3x y. That is what you have to substitute in the third row. This thing is 0 because 2 rows are 0. So what you have is, once you substitute, when you replace y1 triple dash, y1, y2, y3 are satisfying this equation. Okay. So when you replace y1 triple dash minus a1x y1 double dash, okay, this is the only term that will contribute, because when you substitute this one a2 minus a2x y1 dash, if you put it, because I already have minus y dash, similarly you are going to replace here. Okay, so if you let us do it, so let me take, it takes little time, but it's fine. y1 dash, y2 dash, y3 dash. Now you can replace each of this as minus a1x y2 dash, y2 double dash, minus a2x, okay, and minus a2x y1, sorry, it's y1 double dash, y1 dash. This is only third row, third row, first column. So minus a3 of x into y1. And similarly, you replace minus a1 y2 double dash minus a2 y1 double dash minus a3 y2
y2. Similarly, the last element is minus a1 y3 double dash minus a2 y3 dash minus a3 y3 just y3. Okay. So, this is equal to, you can split this into 3 determinants. Okay. One is y1 y2 y3 y1 dash y2 dash y3 dash, and this is going to be minus a1x y1 double dash minus a1 y2 double dash minus a1 y3 double dash. So, each of this, one here, one here, one here, and then rest is same. So, again y1 y2 y3 y1 dash y2 dash y3 dash. So, here you pick up this one, these 3 elements. So, you have minus a2 y1 dash minus a2 y2 dash minus a2 y3 dash. These are same because a2 is constant function of x, which you can take it out, then the second row, third rows are same, this is 0. Similarly, the last one y1 y2 y3 y1 dash y2 dash y3 dash, and this last one is minus a3 y1 minus a3 y2 minus a3 y3. So, this is also, because the first row and last row are same, is 0. So, what you are left with is minus a, you take it out, minus a1 of x, and this determinant with, once you take this minus a1 out, whatever is the determinant is wx. So, this is your dw by dx. So, this implies wx equal to, like earlier you integrate from x naught to x naught belongs to the domain of the differential equation. So, you have this w at x naught e power minus integral x naught to x naught to x a1 of t dt. So, this is your formula for Abel's formula. This is your Abel's formula for third order linear homogeneous equation. If you know y1 y2 are 3 solutions, three solutions, this is what you will get. This Wronskian you can write like this. Now, if these 3 solutions they are linearly dependent, we have seen that the Wronskian at some point will be 0, then it is 0 everywhere. Okay, because w at x naught is 0. If they are dependent, w at x naught is 0 at some point. Okay, so x naught is arbitrary. I can pick up this x naught as that point where this Wronskian is 0. So, if this is 0, then the Wronskian is 0 because the exponential function is non-zero everywhere for all x. So, this is 0. So, this implies that is the property, that is Abel's property 3 is Abel's formula, and you have Wronskian of if the Wronskian is 0 non-zero at some point, then Wronskian is 0. Wronskian is 0 for every x or non-zero for every x. That is the property 3. So, fourth property is, if you know that if you are you do not know how to find. So, what is the fourth property for the second order equations you have done is, the second order linear homogeneous equation will have only 2 solutions. Okay. So, here nth order equation will have only n linearly independent solutions. So, proof is exactly the same. So, what you do is you consider first your y1. Okay. So, your y1 is a solution. Here again, here we have to make use of the existence uniqueness theorem for the nth order differential equation. So, let us consider the nth order differential equation Ly equal to 0, which is equivalent to, so again I will give you without proof this theorem with a1s, all ai of x are continuous in R. Then this Ly equal to 0 with the initial values, y at x naught is let me give alpha 1, y at x2, y dash at x naught is alpha 2, y at n minus 1th derivative of x naught initial value is equal to alpha n. So, this initial value problem has a unique solution, yx. Okay, we will have for every x in R. If your domain is R, you will have that R because it is a linear system. Okay. So, this you can take without proof. With this theorem, if you apply, now consider the initial values, okay, alpha 1, alpha 2, alpha n. You consider this as 1, 0, 0, everywhere 0. If I choose this, I will have one solution, which is a unique solution. Apply the theorem, you will get y1. Okay. So, what is this one? So, if you choose this, if I choose, so this is like this, if I choose like this and so on, if I choose alpha 1, alpha 2, alpha n like 0, 0, 0, ith position I take 1, otherwise 0, 0, 0. If I choose like this, I get y of x. Like this, you can choose I is from 1 to onwards n, because I have n elements here. So, you have n linearly independent solutions. Why they are linearly independent? Because if you make Wronskian out of all these solutions at this initial value, what is the Wronskian? Wronskian is Wronskian at x naught, Wronskian of this y1, y2, yn at x naught is actually equal to, what is the Wronskian? y1 at x naught, that is 1 0 0, 1 0 0 0 0. Other one y2 will be 0 1 0 0 0. Like that you go on 0 0 0 everywhere, 0 last is 1. So, this Wronskian is the determinant of this matrix. Okay. This is equal to 1, which is non-zero. Okay. Because this is non-zero implies Wronskian implies y1 y2 are yn are linearly independent. You cannot write any one of them in terms of the other, that is the meaning. Okay. So, you have n such solutions. Okay. So, how do you know that there is these are the only solutions? Suppose you have any other solution. Okay. So, just like the proof is same way that we have done for second order. Let phi be any solution, phi x be any solution, any solution. If its solution of Ly equal to 0, that means it has n derivatives. I can calculate phi at x naught, okay, phi at x naught, phi dash at x naught up to phi n minus 1 derivatives at x naught. You call them as alpha 1, alpha 2, alpha n. Okay. You calculate. So, once you have this, then phi x, any solutions, phi x is satisfying the equation with this initial condition. Okay. Then I consider yx as alpha 1 y1 of x plus alpha 2 y2 of x and so on, alpha n yn of x. Then what happens to my alpha y at x naught? So, this is a linear combination satisfies Ly equal to 0. So, what are the initial conditions? Y at x naught is alpha 1 times y1 at x naught is 1, y1 dash at x naught is 0. Okay. So, you will have only 1. If I calculate its derivative y dash, I have alpha 1 y1 dash, y2 dash of at x naught will be 1. So, that will have y dash at x naught will be alpha 2. Like that y n minus 1th derivative at x naught will be alpha n. So, you have two such solutions, y is satisfying the same initial values, phi is having the same initial values. That implies any solution phi should be your yx, that is actually a linear combination of your yi alpha I is from 1 to n. So, if you have a solution whose initial values are alpha 1, alpha 2, alpha n, you take the linear combination of yi's with these alpha i's, that is actually the solution. Okay. So, these are the only linearly independent solutions. So, that implies these are the only linearly independent solutions. Or in another statement, Ly equal to 0 has only n linearly independent solutions. Solutions y1, y2, yn. Okay. This you can choose anything. So, instead of 1 0 0 0 0, you can choose 2 0 0 0, otherwise for y2 initial values are 0 2 0 0. Like that, based on the, you choose your initial values as vectors in Rn, which are n linearly independent vectors, then you corresponding solutions, initial value problem with those initial values, you will have n linearly independent solutions, okay, and any solution you can write in terms of them, but in a different form. So finally you can say that Ly equal to 0 has n linearly independent solutions, okay. I am not saying these are the only n linearly independent solutions, so it will have n linear. This is the property number 4, okay. So the only thing we used for the second order is this Wronskian, this Abel's formula. Abel's formula, through Abel's formula, if you know one solution, you can find the other, because there are only two linearly independent solutions. But here we cannot, because if you use this Abel's formula, if you know one solution, you can reduce the equation into one level down. So you will have n, you can reduce nth order equation into n minus 1th order equation, okay. So you should be able to know n minus 1th order differential equation, linear homogeneous equation, then only it is useful, okay, because it is for second order. If you know one solution, it will become first order equation, reduction equation will be first order, which you know how to solve certain method, because linear equation you know how to solve, so you solved it, get your second solution y2. In this here, nth order equation, if you are given one solution, all other solutions will be satisfying n minus 1th order differential equation, that you should be able to know. Only if you know, you can find all the n linearly independent solutions, otherwise you don't know, okay. So that is really not useful, that property. So let us see for higher order equations. These are your higher order equations. What are the for the second order case, we can also solve any nth order homogeneous higher order equation. Let me take only third order things, okay. Let me take only third order equations. So equations, third order equations, okay, third order or nth order equation, third order linear homogeneous equations. Equation with constant coefficients. If your coefficients are constants for this third order equation, y triple dash plus a y double dash, a is constant, b y dash plus c y equal to 0, where a, b, c are constants, okay. If these are your okay, if this is your domain and I is your domain, which is part of the real line, and a, b, c are constants, then again how do I find the solutions? E power lambda x, okay. Because the linear equation has the form e power lambda x, so you can check whether this is a solution. If you substitute there, you will have 3 derivatives of e power lambda is lambda cube e power lambda x, plus a is constant, 2 derivatives of e power lambda x is e power a lambda square, b is a constant, 1 derivative is lambda into e power lambda x, plus c into e power lambda x. In the place of this has to be satisfied. So this will give me, because e power lambda x cannot be 0 both sides, so this has to be 0. So that means lambda 3 plus a lambda square plus b lambda plus c equal to 0. So you have this is a polynomial equation of degree 3. So you have 3 roots, which are lambda 1, lambda 2, lambda 3. If they are all distinct, okay, so you have two cases, lambda 1 is not equal to lambda 2 is not equal to lambda 3, then e power lambda 1 x, e power lambda 2 x, e power lambda 3 x are linearly independent solutions. Clear, right? Because these are any two you pick up, they are linearly independent, because lambda 1, lambda 2, lambda 3 are distinct, okay. So you cannot make any combination with the non-zero coefficients for which this combination will be 0, except this coefficient has to be 0. That means they are linearly independent. If they are different, lambda 1, you have two cases. One is this. Second case is any two or all of them are same. So lambda 1 equal to lambda 2 and lambda 3 is different from, it's not equal to lambda 1, okay, or lambda 2. So if this is case, or lambda 1 equal to lambda 2 equal to lambda 3. So, any 2 are same or 3 are same. In such a case, you have seen that e power lambda 1x and e power lambda, in this case e power lambda 3x are linearly independent because lambda 1 lambda 3 are different. But you also have seen that if there are two roots, repeated roots, x into that e power lambda 1x is also a solution. You can see this after substituting into the equation, you can see that because the polynomial is this, if it is repeated, the polynomial can be written as lambda minus lambda 1 square into lambda minus lambda 3. You differentiate with respect to lambda and put lambda equal to lambda 1, it is also 0. So, that makes it, you can see that using that, you can see that x into e power lambda 1x is also a solution. Okay. So, this is one solution. If it is repeated, x into e power n is another solution. And third one is because it is repeated. Okay. And this is in this case. So, in this case what happens? E power lambda 1x, and now you can verify x into e power lambda 1x is also a solution, x square into e power lambda 1x is also a solution, because because the roots are same, the polynomial will be lambda minus lambda 1 cube equal to 0. Okay, polynomial is this. So, if you differentiate this lambda and put lambda equal to lambda 1 is also 0, and you differentiate twice, put lambda equal to lambda 1, that is also 0. So, whatever comes when you substitute this into the equation, all the three. Okay. So, if I say these are the derivatives, I is from 0, 1, 2. So, all these three expressions you will be are 0, which are coming into the picture once you substitute this. If you substitute this, you may get only 2 of them, I equal to 0, 2 you will get here if you substitute this. If you substitute this, you will see only 0. If you substitute the last one, you will see all three of them will come into picture. Okay. Once you substitute this into the equation, because all these three are 0, so it will be, equation will be 0. Okay. That means this is the solution. So, if the three roots are repeated, you simply multiply 1x x square into that e power that. So, like that you can get your 3 linearly independent, and because these three, 1 into this, x into this, x square into exponential, these are all linearly independent clearly. Okay. These are linearly independent functions, they are solutions, they are linearly independent solutions. This is how you can get n linearly independent solutions for the nth order linear homogeneous equation. Okay. So, for the problems we can only see, only what is challenging is to find the roots of the nth degree polynomial, which you all a priori know all the roots. It is not easy. Okay. If you are given nth order equation with constant coefficients, substitute e power lambda x, you will get a polynomial lambda of nth degree. Nth degree polynomial equation may be difficult to find the roots. Okay. So, the problems you can do in practice you can do third order or fourth order, so that you can find solutions of the third degree or fourth degree polynomial. Okay. So, let us give an example of some higher order equations. Y double dash, y triple dash minus 5y double dash 6y dash equal to 0, some simple one. Okay. You try to solve this equation. So, what I do, this is the equation with higher order equation with constant coefficients. Okay, nothing is given means x is full R. So, let y of x, you look for a solution of the form e power lambda x. Then like earlier, you have your lambda cube minus 5 lambda plus 6 equal to 0, 6 lambda equal to 0. This is lambda square. Okay. This implies lambda into lambda square plus minus 5 lambda plus 6 equal to 0. So, what are the roots here? So, lambda minus 2, lambda minus 3, you can easily find. Okay. This is a quadratic equation, you know how to find the roots. Okay. So, you can do this, minus 2 minus 3, so you have minus 5, 2 into 3, 6, so it is easy. So, you have these are the roots, lambda is 0, 2, 3. Okay. Once you have these 3 roots, they are all distinct. So, you have y1x is e power 0x, that is 1, y2x is e power 2x, y3x is e power 3x, are linearly independent solutions of third order equation. So, these are the only equations we know from the property. So, that implies the general solution is Yx, you can write as a linear combination of this C1 times Y1 1 plus C2 times e power 2x plus C3 times e power 3x, where C1, C2, C3 are arbitrary constants. Okay. So, you can also do with equal roots like earlier, it is not a difficult thing. So, just cook up instead of taking some simple thing. So, you can have a lambda minus 2 whole cube equal to 0. What is the polynomial you will get? Lambda cube minus, what do you get? So, the best way is lambda minus 2 lambda square minus 4 lambda less 4 equal to 0. So, this will give me lambda cube minus 2 lambda square minus 6 lambda square, then plus 8 lambda plus 4 lambda plus 12 lambda, okay, minus 8 equal to 0, right. So, if this is what you want as a polynomial equation, so you can guess the equation, okay. So, you can guess the equation. This is how you can cook up, okay, problems. So, I can give you solve y triple dash whenever you get the lambda cube minus 6 y double dash plus 12 y dash whenever lambda is there minus 8 whenever there is a simply constant you put y equal to 0, okay, x belongs to R. So, if you are given like this beforehand I know this, okay, that is why I make this equation. Otherwise, if I start with this, I have to worry about the roots of this, that you know, you can guess, okay, you can find out by guessing 1, 2, 3 like that. You can check, verify and see that there are roots. Once you know one root, you can divide that third order polynomial equation into, you divide with that root, you can make it second order, second degree polynomial equation, whose roots you know how to find, okay. So, this I leave it as an elementary thing, you yourself can find out how to do that. So, this as a solution, we always look for the solution in this form e power lambda x, then lambda satisfies lambda cube minus 6 lambda square plus 12 lambda minus 8 is 0. That we know already, that is. So, assume that I know. So, this will have lambda equal to 2, 2, 2, 3 repeated roots. So, the general solution I am directly writing C1 e power lambda x 2x plus x into e power 2x. So, make another constant x into e power 2x plus C3 x square e power 2x, which is C1 plus C2x plus C3 x square into e power 2x. This is your general solution, okay. This is how you can see the roots are repeated, some of the roots are repeated, you can write, you know how to find and linearly independent solutions. If it is third order, 3 linearly independent solutions. Finally, if you want a general solution, just find the linear combination of all these linearly independent solutions. I will give you the general solution, okay. So, this is how we use this in the later chapters, later videos, where you see that. So, we will use this method when we use when you are trying to find the next videos, when you are trying to find the non-homogeneous, when you are trying to solve the non-homogeneous equation, linear equation, okay. What you need is, if you know all the linearly independent solutions of homogeneous equation, then and a particular solution of the given equation, non-homogeneous equation, then the sum of these two, general solution of homogeneous equation and a particular solution together will be the general solution of a non-homogeneous equation, okay. So, if you want to solve the non-homogeneous equation, you should have general solution of the homogeneous equation. So, homogeneous equation with constant coefficients, you know. If you have to, so what are the other type of equations for which you can find the general solution? when the equation is non-homogeneous, when the equation is homogeneous. Okay. So, the next video will give such methods. For example, when the coefficients are not just constants but in certain form. Okay. Nth derivative is having an x power n coefficient, n minus 1th derivative will have x power n minus 1. Like that, if you have, it is called Euler-Cauchy equation, we know how to solve it. Similarly, sometimes you can reduce some equation, second order equation into normal form, remove the n minus 1th derivative, that means first derivative we remove. In the second order equation, first derivative you can remove with the transformation. Then it will become, you can hope the equation to become a second order equation with constant coefficients. Okay. So, that way it works only very few equations, but that you can learn, so that you can find the general solution of the homogeneous equation. So, for such an equations, if your non-homogeneous term is given, you only have to find a particular solution, so that the general solution of the homogeneous equation plus this particular solution together will give me general solution of the non-homogeneous linear equation. Okay. So, that we will see in the next video.